So we're going to start with the official part of the meeting. I know some people are still eating a little bit, but I don't think it should interfere. What I want to do is I'll recognize, we have 2 Teachers of the Year. The Teacher of the Year to me is very significant. You know, they help students in my mind. Yeah, they're focused on STEM, and that's important. That's very important. And so I want to give each of them, I could read their bios and what have you, but I'd rather give them each a chance to come up, say a few words. Mark, I got to keep looking at the name to make sure. Mark Donato brought some materials with him. So, Mark, if you want to come up and get your award, and then you can say.
You want to take photos now?
Take photos?
Or you want to take it later?
Let's take photos later.
Later.
Yeah. So, Mark, well, we're on videotape, so just
There you go.
congratulations, and outstanding, and we hope you decide to stick with the AFA, like Frank has, and I'll give you the floor to say a few words.
Is this where you'd like me to speak a little about what I did?
Yes, yes,
Let's
yes.
do it.
You could raise that mic up if you want.
Let's see. Bump it up like that. There we go. Okay. Wow, thank you. Thank you so much. So as I had mentioned before, this came as a complete surprise to me, very happy surprise. My supervisor got in touch with me a couple months ago, and he said, Mark, I need you to just if you could just write up a 1-page paper about your different activities, how you run your STEM room, that sort of thing. I need to submit it for QSAC. You know, they're coming in, they're checking the schools out. It's like, yeah, okay. You know, so I sat down, I made sure, hammered the whole thing out, gave it to him. Seemed a little weird because I've never had to do that for QSAC before, but I was like, okay, sure. Then he got in touch with me a month later and he said, okay, Mark, so I lied. This was not for QSAC. This was for the Air Force Association STEM Teacher of the Year, and you won. It's basically like the New Jersey Quality Assurance. They come in and they make sure the school is functioning correctly and like that sort of thing.
Like Nate.
What's that?
Like Nate? National Association of Industrial Technology?
Not quite. It's more so like a general, you know, making sure that there aren't exposed wires and like, you know, there's nothing is stocked up too high above towards the ceiling, right? You know what I'm talking about. Yeah. So it's just a thing that happens every few years. So, but it was not for that. It was for this. And he said, and you won. So this was really exciting that this happened. So I actually took just a couple of notes so I can stay focused. I'm a very scatterbrained person. But like I said, I am the STEM teacher. Face this one. So I am the STEM teacher at the Jefferson Township Middle School, and I've been there for 4 years now. And the most important thing, the most important part of my class isn't any of the specific details. Because when we think back to school, you don't remember a lot of the specific details of things you learned for tests and things like that. I used to know every single Roman emperor in order because I needed to for a test. I don't remember like any of them now. There's a small handful. But so I think the most important thing is that you are teaching a mindset. You are teaching something that they can take with them into any field that they go into. Something that can be used professionally, something that can be used personally. So the main thing that my class is focused on is the 7 steps of engineering and how you can use them for pretty much anything. And that is the main focus. It's honestly more important than any of the actual projects themselves. The projects can be interchanged, they can be swapped out with more current things, but that idea of being able to break down what you are doing into those 7 steps in order to solve a problem is so incredibly important. Because you never entirely know where you're going to wind up. So you want something that is fully usable everywhere.
Are you going to tell us what they are? You're handing something out, maybe?
Of course, I have them here. So let me come and.
Oh, you don't have them memorized?
What's that?
You don't have them memorized?
Oh, I have them.
STEM teachers in science and math.
All right. So what's really great too about having these 7 steps is that once the kids have gone through one project, they know these steps now. And when you move through other ones, they're able to move a lot quicker, and they're able to move autonomously, which is such an important thing in a STEM room, in engineering, is the fact that the kids can pretty much do it themselves at this point. Obviously, you're still helping, you're guiding them, but they're able to move on. They're not stuck waiting. They're able to move on, because if you want their creativity to keep flowing, you don't want to keep stopping them. You want them to be able to go, okay, I finished step 3, I'm ready for step 4, and they can just move on, and they can start working through that problem. And what's really great too is the way our school is set up. It's 6, 7, 8 is who I teach. The 6th graders, we have them for 30 days, and that's it, because they try out every single elective. And then in 7th and 8th grade, they get to choose which one they want to take. So what's wonderful is you introduce them to those steps in 6th grade, and then you have the kids that are really excited to come back in 7th and 8th, and they already know the steps, and they're already ready to go, which is fantastic that it's set up that way. And that, like I said, that autonomous nature is so important to let them explore, let them discover. And you hear a lot about teaching and how we're trying to promote inquiry, we're trying to promote curiosity, that sort of thing. You don't really have to promote it. Kids have it. They're curious. They want to try stuff. They want to use their hands. The problem is sometimes us teachers don't want to let them do it. We don't want to let them off the leash. And that's what you have to do. And it's a scary thought. And obviously you still have some parameters, they're not swinging around on the ceiling fans and stuff. But you want to let them go creatively. You want to let them find and discover their own things. So if they have an idea for how to solve a problem or something they want to do with their project, I very rarely say no, unless there is an actual good reason. I have to tell them no. And some of the best projects that they've given me, the best designs they've come up with, is because they came up with something off the wall and you let them do it. And especially when it comes to them trying new things, us as teachers sometimes have a nasty habit where if a kid is trying something, right, they're tinkering around with something, and it's not going to work, right, because you've done something similar, it's not going to work. We immediately want to rush in and be like, no, don't do that, it's not going to work, here, try this instead, right? You have to let them make that mistake. Because then you're going to remember it, because when you remember making a mistake, you remember what you did afterwards, and you're like, that didn't work, okay, wait, what if I try this instead? And only if they're really stuck do you kind of come in and try to kind of push them a little bit, goad them a little bit to help them out. So these are the 7 steps that I have them do with every single project. So step 1 is you develop a question. And it's something that you're doing with the entire class. We're all doing it together. And the important parts here are, why am I doing this? Because your design is going to change based on why you're making something, right? If you want something to be fast, you're going to make it more aerodynamic. If you want something that is meant to retain heat, you're going to make sure it's more insulated, right? So the purpose of why you're making something changes what it's going to look like. And another thing is, what are the restraints that I still have? Because as engineers, you're never put in a real life scenario where you're told, okay, do whatever you want, literally anything, right? There's budget, there's time, there's size parameters. So you put some on there to make it challenging, and then you let them do whatever they want to do within those. And together they develop a question of how can we, and in that question they put all the stuff that they need to keep in mind, all the stuff they're trying to accomplish, and that's step 1, they've all done it together. Step 2 is they're doing research. So the 2 main questions there are, has someone tried this before and did it work? And what do I need to know before I get started? And that's something they do on their own, and I'll explain why later, but they research on their own. Then they move into brainstorming, that's step 3. And this is where they start working on technical drawings. And I start teaching them things like scale, how scale works. You're drawing something, which is really difficult with 6th graders, for them to understand the idea of, I'm drawing something here that is realistically this size, but I have to draw it here, right? So that's a difficult thing. But being able to add on those engineering notes and their dimensions for different parts, And not just make a blueprint, but they also do something else next to it where they're talking about why this is going to work. What are the design choices they put in here on why they think this brainstorm is going to work? This is also something they're doing on their own. They move into step 4. That's planned together. That's when they start working with their partners. They picked out partners earlier on. When they're planning together, they take all that research they found and all those blueprints they made while brainstorming, and now they are showing them to the other people that are there. They're almost presenting their information that they have. And together, they come up with their final idea of this is what we're going to try to build. So you hear all this discussion where they're all going over, okay, I really like this part of this, I'm not sure how much that's going to work, why did you put this in here? And they all almost Frankenstein something together, where this is what we're going to end up doing, this is what we're making. And the reason I really like to keep them separate up until this point is because if you have kids that are like really shy, or not so confident in what they've made, if you just immediately put them in groups and say, okay, figure out what you're going to make, that shy kid is not going to say a single thing. They could have the most brilliant idea ever, they're not going to say it. So when you give them that opportunity of you're preparing your stuff in advance and then you can show it with your group, even if they don't want to talk, they have their entire design they made. They have their rationale for why they made different things. The other kids are able to see that and go, oh, that looks really good. And then you have those shyer kids start opening up, because now it's like this thing they've made that these other kids are interested in. Now, you know, they start talking about it and they come up with that design together. Step 5, they start building it. And sometimes with 6th graders, right, when they're not familiar with the process, their immediate thought is, okay, well, when do we start the project? Because in their mind, building it is the project, right? So you have to show them earlier on, no, you have to get there first. These are all things that are running through your brain. You might not know they're running through your brain, but they are. So then when they start getting familiar, they understand, okay, well, I'm actually doing all this stuff in here before I even start building. So now it's just letting them know, letting them see what they were doing. And when they build it, if I don't have a material that they want to bring in, I let them do it. And I've gotten some really interesting ideas come out of that. From just, yeah, well, what if we use magnets on this thing? Or what if we, anything like that. Let them go for it. Step 6 is when they test it out. So we have a big testing day, it's a lot of fun. We have all the groups come together, they're all showing off their designs that they made. Kids are allowed to ask that group questions about their design. Why'd you do this? Why'd you do that? While they're showing off how their design works. And then lastly, which is told as the most important step, is improving it. So you took your design, you wrote out how it performed, right? You wrote all that data out. This was how it did. You put that data sheet down, you put your project nearby, and then what other kids are allowed to do during step 7 is they are able to walk around and see how every single one of the projects fared. Even the ones that weren't in their class period, they have that result sheet taped on it or in front of it. And then what they start doing is they start going around, and step 7 is, okay, if you were to do this again, what would you do this time? Based on how everyone tested, based on how you tested, what would you do? So you have all these kids that are going around, they're looking at the other projects, they're saying, oh, I really like that design choice that was made there. They're heading back to their seat, they're starting to workshop more stuff together. And that is the final step of them making that blueprint 2.0. If I did it again, this is what it would look like. So those are the 7 steps that they are working through. And one thing that I always try to instill in them, and this is kind of a problem that you've probably faced a lot too, this is just kind of a societal norm, is a lot of times when you want to take a risk, you want to try something, there is this viewpoint in society of, if you try out that new thing and it doesn't pan out the way you wanted, that's bad and you failed and you should be embarrassed about it. Right? That's just, it really is just a general stigma, right? And if you really want kids into engineering, they need to know that you didn't do a bad thing, you just found a way that didn't work. Which, as long as you record that down, as long as you remember that, that can be almost as good as finding a way that did. Sometimes that can be better than finding a way that did, because it makes you think harder. You say, okay, this really didn't work. Why didn't it work? What specifically didn't work? And you'll have kids that come in and they'll hear what the challenge is that you're setting for them, right? And their first thought will be, they'll get really panicked, they'll come up to you and they'll say, if we don't figure out how to do this, do we fail? And it's like, well, you gotta change that mindset. You gotta let them know that the process is more important than whether or not you did it. How did you get there? How did it do? Not in the sense of, did it do well, but did you write down how it did? And then if you were to do it again, how would you improve it? That's what's more important, is getting into that mindset of all of this, successful or unsuccessful, it's showing me how to improve it, and that's the most important part in engineering, is finding something that works better. So whenever they fail, you want to tell them that's not a bad thing. All they did was find another interesting lesson. And that's something I showed them at the beginning. Thank you.
Exactly.
Yeah.
Exactly what Thomas Edison did.
Bob, come back up here.
Oh,
You want to, I gotta give you the rest of it.
man, I almost got away too.
Yeah, almost. So let's see. Okay, so the rest of your record, you get a folder, you get a pin you can wear proudly, and there's a check in there.
I didn't know there'd be so many prizes.
You want to pose? You want to pose there?
Sure.
Why don't you move that?
Can you get the flag?
The flag too. Okay, thank you very much.
Howard, take another photo.
Oh, yeah, sure.
Marlena?
Yes.
Stay next to you.
Sure,
I should have a chair to stand on.
That's great, that's great.
Oh, great.
That's great. Okay, thank you.
Thank you.
Is there a written quiz?
Yeah.
Okay, you can now go sit down.
Oh, now I can.
Now we're done with you.
Good job.
There is a written quiz. What was step 4?
So wait a minute, now who developed those steps? Was it Descartes? Who developed those steps originally? Was it Descartes? I think it was Descartes, wasn't it, the philosopher?
They're not new. I can't take
No,
credit
they've
for
been
making
around
them.
for a long time, but that's good. All right, so now,
Oh, you have a
Do
question?
they ever come to the conclusion that the project can never work, that they picked something that was unworkable?
You know, I have had students where their particular way of going about it, they have reached that conclusion of, this won't work. At which point, I have seen students be able to salvage things and actually get them to work, which is fantastic. But again, right, there's a lot of frustration that happens. So you want to make sure to really instill that you're discovering something all the time, right? You didn't bomb this. You just found something that didn't work. So take what you have here, or take some new stuff you can add, and find a way that does. Yeah.
Quickie, I was impressed, as you were talking, I was thinking, hey, this is the way you want to bring up a child. Like your own child. Be open with them rather than constricting. So I saw that commonality.
Well, thank you. Yeah, I was actually listening to something very interesting by Neil deGrasse Tyson this morning, and he brought up this great point where he was talking about raising kids, and he said at one point he was sitting in a park, and there was a mom walking by, and she had like a 3-year-old kid with her, and the little kid, he had his galoshes on, he had his raincoat, right, and there was a big puddle in front of them, and his thought was, let that kid jump in that puddle. Because you know what? If that kid jumps in that puddle, he's going to see how like force interacts with a fluid. He's going to see how the water ripples around. Like that's a discovery that 3-year-old is going to make, right? And the mom took the toddler's hand and walked him around the puddle. So the idea of just letting them loose.
Yeah.
You know, you want to let them explore. You want to let them create. Don't give them so much restriction that they can't do that.
I wish more parents were that way.
So
There are some restrictive parents.
Jim, we'd like to let you continue, but we need to hear from
Sorry.
Mark Meola, our other teacher of the year. And come on up, Mark. And Mark has brought books, actually, engineering books, very interesting. And I don't know what his plan is, to circulate them or just hold them on?
Yeah, I think I might let them go around so people can see student work.
Okay.
Can you use the microphone again? We can't
I
hear
will.
down here. Thank you.
Okay. So, Mark, our other teacher of the year, congratulations.
Well, thank you.
And I will, when you're done, I'll come back up, we'll do a photo, and we'll
Okay.
invite your lovely wife up, and we've got a couple other things for you also.
Okay.
You're on your own.
All right, thank you. So the only thing I'm going to pass around at this point in time are a couple of examples of, I'm going to pass around a couple of examples of student work. And so I'm going to get into the breakdown of what's my program all about, how does it work, what do the kids accomplish, you know, how does it apply to all students and not just students that are necessarily going towards engineering, but also how does it enable students who are interested in engineering to achieve their goals. I'm going to show you some examples of works of teams that have accomplished really great things. So I'll pass them around and you can kind of look through them at your leisure while I'm yakking up here. And the red book represents the team that was #1 in the state of New Jersey in 2019. The second book here is an example of a team that went to the World Championship this year. Actually took first place in design in the state of New Jersey, and that's what got them to Worlds. And so you'll take a look at their work as I talk about some broader things.
I have to say, I love the young people with their talks on their cell phones. You know, where have we come from?
Well, I really appreciate that compliment, I have to say. Considering I'm about 6 years away from retirement, but we'll go with that.
You're a lot younger than me.
All right, so first off, I want to say thank you to the AFA, Chapter 195, for this award. It's greatly appreciated. And I would say it's greatly appreciated for this reason, is I have a great deal of respect for you, gentlemen and ladies, from this perspective. I grew up as a child of a World War II veteran, and I very much esteem the opinions and thoughts of that generation. And I think you people really know what's important and what we need to be focused on. And for you to take the time and to give recognition for work that's actually going into enabling the young people of our country to achieve great things and to make our country a great place, I think it really speaks to the work you're doing, and so that's why this honor means something special to me. So to get more specific, a little bit about the program. As I mentioned earlier, I was in industry for 17 years, worked right up here on Columbia Turnpike, and eventually found my way into education, where I've been for the last 23 years. And I teach technology education, and now more specific, robotics and engineering. So to talk a little bit about the program itself, started off, very small. I had the opportunity to come up with an idea that I thought would affect the student population most profoundly, and so robotics was a great opportunity to do that. It's something that enables kids to get excited about and learn without the formality necessarily of the classroom setting, the academic rigor. Not that it's not present, but my point is it's hands-on, but it also has academic rigor, and it takes that academic rigor and gives it a real-world opportunity, something to actually do with that knowledge and training. So anyway, to talk a little bit about the program itself, this year we've gone from about 10 students 12 years ago up to about 123 kids that are involved in the program now. There are a number of classes that I had the opportunity to create over the years. The current classes that I'm teaching have to do with very much what Mark talked about, some foundational stuff as far as design process, technical literacy. These sorts of things are really kind of the underlying themes, because not every student aspires to be an engineer, but it doesn't mean every student shouldn't be technically literate. And so there's a part of the program that really focuses in on enabling all students to feel comfortable with technology. We live in a technological world, and I think this group is unique because of your experience in the military and in the Air Force in particular, which is more of a high-tech area of service. But by and large, there are a lot of people that would be in your age that would be very intimidated and have really kind of come through a rough time of all of the technical evolution that we've gone through. Well, kids may seem like they're able to, just step right into it. Well, they're really not. I like to say that kids are great consumers of technology, but the goal really is to make them inventors of technology, not to just be content with being able to use this thing and, and this is impressive, right? Well, it's not really. It's just a device. It's just like a computer. It's just in my hand. And, we're all comfortable with that, and we want to get kids to the point where they're not just content to be users, but they're actually more interested in being creators. Right? And so I really appreciate what Mark said earlier about laying the foundation of design process thinking. At the high school level, it kind of evolves into the next step. It can be applied to any area of interest. It could be just day-to-day living, as far as how do you approach life? Do you define your problem first? Do you research what you need to know? Do you develop solutions before you decide what you're going to build, and so on? Well, it's especially true in the engineering world. So we let kids learn that foundational stuff, and then that's kind of an underlying theme through all of my programs as well. So one of the early classes that I teach is called Intro to Engineering. And in that class, it's sort of an a la carte experience. They get exposed to a number of engineering areas, but with the theme that underlies it of design process or process-driven design. So in that particular class, there's a couple of topics that we cover. Initially, it's just design. Let me go to my notes just to make sure I cover everything that I intended to. So what is engineering? What is process-driven design? Expanding technical literacy. We move into engineered materials and design. That's kind of my background. So I make sure I infuse a little bit of that firsthand knowledge. We look at civil engineering and a variety of things related to civil engineering. We look at aerospace engineering. My kids are doing a project right now in aerospace where we cover a number of topics as far as things that would bring that world to light for them. In addition to aerospace engineering, we do things in 3D CAD design and simulation and prototyping, and then lastly we cover manufacturing and process control. So that's all in an introduction to engineering. Most kids, they don't understand what engineering is at all, right? And so to define that for them, put understandable terms and occupations, and that's what my father does. Sometimes that's the reality of what comes about in that moment of discovery. But to also go into the depth, or at least a depth that is understandable for where they are at that point in their lives, it really kind of opens up opportunity, right? It really opens them up to consider things that they may not have considered before. Some kids, if it's hard, they don't want to do it, right? So how do you get them past that? How do you take that math class and make it more applicable so it's not just the rigor of learning the math, but they see the real application of it in a way that produces something that, hey, that's tangible, it's understandable, it does something, and they can relate to that. So that's my intro class. I also have an introduction to robotics. It's actually called Robotics Engineering 1. And in Robotics Engineering 1, they learn mechanical systems, motors and sensors. They are introduced to computer science through block coding. They also, again, as an underlying theme, it's process-driven design, and they do in-class competitions. So just like in the real world, industry is driven by competition, right? To the winner goes the spoils, and so we kind of use that as a theme within the class. We compete, and competition drives ideas. I mean, throughout our history, unfortunately, things like war have really driven the whole design process to create new and innovative things. The space program has actually been a big, impetus in moving that forward and creating great technology. And so competition plays a fundamental role in what I do. The second level, Robotics Engineering 2, is a little bit different in that it is advanced mechanical design. We move from using block coding to using C++ coding. So the kids are actually learning coding that's industry specific to actually control the function of a machine. Again, it is also competition driven, but in this instance, it's not just against their classmates, it's against other schools. So there's an organization called the REC Foundation, and they are the sponsors of a robotics competition that we are very much involved in. Now, there's a number of great robotics competitions out there for high school age kids. I chose this one because I think it gave the kids the greatest opportunity to have hands-on, for them to be the creators of the technology. And so that is a part of that second level robotics course where they actually use design process to drive forward ideas, create a robot that they compete against other schools, and then there's this whole iterative process where they continue to improve their design so they can get better. They can get better against the competition that's out there. We teach them Autodesk Inventor because we do a lot of 3D modeling. They learn that it is easier than to just jump ahead. So to back up a step, you know, when we were kids, or maybe when you were kids, you were given a bucket of Legos, and you know, you just dump them on the floor and you build stuff, right? And there's like that creative outlet, not necessarily any direction, but an opportunity to use your mind and your hands and to start doing things creatively. Well, when you move into the engineering world, you know, that needs to become a little bit more organized in order to produce the outcome you're after. And so just jumping ahead and building something without any plan usually produces less than desirable results. I mean, I don't think any of you who were in the Air Force would have stepped into an airplane that somebody just winged, no pun intended, as far as the construction of it, right? There was a process and a method to it. And those are the kinds of things that we're trying to instill in the kids at this particular level. And so they go through an iterative process, which is part of the design process, at least at the high school level, and they improve their design for this out-of-school competition. And what I was getting at is we use Inventor, well, the particular 3D CAD program that we use is Inventor. There are others, but that's the one we focus on because we don't have all the time in the world. We're talking 42 minutes a day that I have with these kids. I can't teach them everything that there is to know about engineering. But what they'll use that for is to test ideas before they actually labor over the construction of the idea, right? We'll see whether it works virtually before we actually labor over building it, only to find out it doesn't work. We can see the range of motion in something, we can see whether the mechanical system will work as imagined, and these sorts of things. And then in the end, we can produce a very accurate technical drawing of that particular design, and then a sub-part of a team can build it. They'll have the instructions, rather than just one person talking to another. I mean, I don't know if you've ever played that game. I do a club called Science Olympiad where we do something called Write It, Do It, and kids sit back to back with each other. The one person has the object in their hands, and the other person has to write the instructions on how to build it, and it's comical, but it is very much a lesson in communication. But if you're really trying to build something technically accurate and reliable and repeatable, you know you have to get your systems under control. And so Inventor really plays a key role in helping us do that. Let's see. So the third level course that I teach is something called Honors Robotics, go figure, right? Keeping with the theme. So what I do initially in that class is we create cross-functional teams, much like I experienced in industry and the engineering world. And they are, again, process-driven design. So they are tackling a problem that they clearly defined first. They research the things they don't understand. They begin the process of developing solutions and so on. So this is very much kind of the evolution of a concept that was mentioned earlier. The coding that we use at that level, we continually try to add in or at least modify. That means my time's up. Either that or place your bets, one or the other. All right, so back to the coding idea. So they already were exposed to C++, they can continue in C++, or now we're evolving it into Python, because Python, again, a coding language that enables the control of a mechanical device through sensors and sensory input. And it's also becoming more of an industry leader as far as what they will experience when they step into the next phase of life, whether it's college or industry. And so we want to expose them to that. 3D CAD, again, plays a big role in this class. Again, competition is a very critical ingredient. One of the engineering journals, actually one of the engineering journals that you're looking at, the black covered one, that is an example of what my World's Accomplishing team this year did 2 years ago. The journal that they wrote this year is still in their possession because of some presentations they have to do related to the process they developed all year long. Because that particular team is part of our STEM Academy. The STEM Academy covers engineering, computer science, and then biomedical engineering. And they go through a whole variety of courses that are focused to give them the background that they need to ready them for college, the next step. And we've had students go to just about every school, every engineering school in the country, and actually 2 military academies in particular. But my point there is that they are presenting, as part of their requirement for this honors robotics class, they have to present the work that they did over the course of the year in the development of their design. And they use that engineering journal. And for those of you who were in industry, especially if you did any kind of research and development, you may remember using a blue book where you had to log what you did in the lab or the kinds of experiments you did to bring a product to fruition. And as a result, they are getting that same kind of exposure. They need to document their process from start to finish. And then they're evaluated on that, not only by us in the school or me on a regular basis as the process develops over time, but they're also judged at competitions. And then at the end of the year, they're judged by a group of teachers. They present their journal and they actually present their robot and a discussion of the whole process. Each member of the team takes the lead on doing that. Another aspect of that program is we do internships. So I've established relationships with several companies. Some of them you'll probably know, Thor Labs in Newton, Murata over in Montvale, Aerojet Rocketdyne down in Carlstadt. Who else are we dealing with? Picatinny Arsenal. And what do we do with these companies? CP Engineering is another local one for civil engineering and environmental engineering. So what do? We give the kids the opportunity to actually go into the workplace and shadow engineers. So it's not just a matter of, okay, I got an idea what engineering is about. I've been taking all these classes to hopefully get into engineering, but I cannot tell you how many kids, unfortunately, go into engineering and then fade out of it because they're overwhelmed by the rigor and what's required of them. So to go into the workplace and see what it looks like after you've accomplished your education and you've received your certifications and your licensing, and here's what it looks like on a day-to-day basis. And so we place these kids with different companies and they do a 20-hour internship so they can experience it firsthand. So again, just to kind of backtrack a little bit, these are for the kids who really are aspiring to go into engineering. We're trying to give them all the opportunity to achieve as much as they can possibly achieve. But in the mix of all of that, there are students who are still just interested in technology and want to be a part of that world as well. They may not necessarily become engineers, but they're being equipped with skills to ready them for technically oriented jobs, which is very much the kinds of jobs that we're going to find most available to them. I'm not the only kind of thing, obviously, but certainly a whole wealth, especially in this particular area of the country that we live in. Oh, let's see here. I talked to you about the culmination project. To give you a little idea of putting in perspective what the teams have accomplished. So the VEX Robotics competition in the state of New Jersey has roughly about 200 teams registered. So the red journal that you're seeing represents our 2019 team that took first place out of those
Can you
teams.
explain the term VEX? What's
VEX, it is a meaningless term.
It is?
Yeah, it's just a name that they chose for the product and the company. But if you look it up, it doesn't mean anything positive. So why they chose it specifically, there's no other, it's not an acronym, it doesn't mean anything more unique. But it is called VEX, VEX Robotics. Okay? Like FIRST Robotics, I know you're involved in that a little bit, or a lot, but FIRST Robotics, much catchier name. And you know, we can, on the side, we can talk about these different organizations and their merits and demerits, but this is the particular one that I'm involved with. And
when you say robotics, for example, I've looked at both of the books now.
Yeah.
up front, it doesn't really say, is that the robotic competition that's on TV? What are they building?
Okay, so that's a good question. So after the World Championships, at the very end of that, they announce a competition for the next season. So it is, for all practical purposes, a game. It is a game that requires a technical solution. And so that's what drives the whole competitive season. And so some schools, they get involved with it and they take their best crack at it and they flounder and so on.
Well, like typically.
Yeah. Well, what would it look like?
Yeah, no, it's, you got, the books look great, but I'm a professional nitpicker.
Sure, go
That
ahead.
doesn't define the problem up front, say, we're building this thing because of.
Okay, so that's exactly what they're required to do. They are required to define the problem. What is the problem? The problem is based on a game. So it's a competition that, for all practical purposes, looks like a game. Just like if you went to a football game and you observed it, and there's rules and regulations and guidelines that dictate what you can and can't do in order to participate. The same is true in a robotics competition. So each team does their best to accomplish what you're seeing there in an engineering journal. Some teams outdo others. All of my students are required to do this, not just the ones who have achieved greater things. So even from my introduction to engineering class, they put together an engineering journal for each of their projects. And what they do is define, they research, they develop, they implement, they test and evaluate, and so on. These are each categories in a technical outline they submit, and there are activities that they actually carry out during the development of whatever solution they're working on. So to get back to your specific question, the VEX Robotics is a competition that's now announced every year. It's based on a 12 by 12 playing field. There are elements that change that are part of the game. There are ways of scoring that are part of the game. And that's what drives the design. Does that answer your question?
What was the object of the game?
So this particular year, the object of the game was to be able to control bases. The field had a number of bases. So this is it's a funny thing. I have this conversation with parents at the beginning of every season because the games are somewhat abstract. To look at it as a first-time person, you'd be like, what in the world are they doing? You have to kind of really digest what's the objective of the game, just like learning any parlor game for that matter. It looks kind of odd until you know why you're doing it, what the strategies are, and what your objective is, and so on. Right? And so this particular year, the field was arrayed with a number of bases. The bases had various height stems, and then there were numerous donut-shaped rings that had a bit of a curvature to them, and they were scattered about the field. And then there were also two platforms that balanced. They were like seesaws on both sides of the field. So what happens is you establish your team, and then you are going to be aligned with an alliance team. When you go to a competition, let's say, I'll use Sparta as an example. I hosted probably the largest robotics competition in the state of New Jersey this year. We had 62 teams attended. Initially, when they're going through qualifier matches to compete in this particular competition, they are aligned with another team from another school. They don't know anything about that team.
But you had to make a vehicle?
Yes.
See, that's the whole point.
Yeah.
They're just supposed to make a vehicle that goes from A to B,
Correct.
up and down.
Correct.
But that's not defined, is it?
Well, it depends on the competition.
Yeah.
But
when you say robotics, that's what
Yeah.
you're talking about.
Yes.
The kids are making vehicles that go from A to B or up and down and do a thing when they get there.
Right.
Okay.
Yes.
Now I got you.
The way they define is usually they're looking at it from a strategic standpoint, and
Yeah,
they're trying to identify criterion constraints in that particular problem that are things that they should focus on by way of design.
The reason maybe it sound a little picky, but in welding, that's my field, welding, robots they have arms and they arm and they go down and they move and they tarp and they weld and they do, that's a robot too.
Right.
The robots you're talking about are vehicles in a sense.
They are absolutely vehicles, yes.
Okay.
Yeah, it's true that in robotics, a large majority of robotics are still in the manufacturing world.
Yeah.
And doing things like welding, but there are other kinds of
right.
applications for robots as well. So the kids get experience with both autonomous control of their robot and then also driver control. So again, we're dealing with kids, so in order to keep it interesting, it's not just an arm sitting on a table that's moving back repetitively like 10,000 times repeating the same procedure. It's completely open-ended. So yes, they are trying to pick up these bases and stack them. They're trying to put rings on top of these bases. they're trying to outdo their opponents. So there's 4 robots on the field at the same time. 2 of the robots are working with each other, and obviously the other side is working against them. They can score and unscore each other, so there's this back and forth that goes on. So what's a part of the dynamic there is that a team would need to go and invest time to learn about your robot so we can compare ability and we can complement each other on the playing field, right? It's sort of like partnering with another company where you have differing technologies that you can bring together for a particular solution. And so they're kind of learning that. So yes, they code it to be autonomous, where the robot goes and does completely on its own to score as much as it can based on the criteria of the competition. And then they also drive the robot to do the same thing, to score as much as they can before the time elapses. The first 15 seconds is autonomous. The next minute and 45 seconds of a 2-minute competition is driver control. Yeah, go
So
ahead.
in the competition, your school may have 2 robots working together?
So my
Or
school,
you might partner with another?
this year I had 7 competitive teams, and they're not guaranteed to be with each other. So at a competition, when they're doing qualifier matches, meaning they're competing to build stats for the day, and at the end of those qualifier matches, they go into a tournament structure, and then that eventually works down to who is the best robot, or who's the best alliance, the 2 robots that work best together. So during the qualifiers, they're randomly put together. There's no control over who they get set up with. So they have to make the best of it. They have to find out the strengths and weaknesses of their opponent, or I should say of their alliance partner in that instance, and they have to make changes in the moment. Like, for example, the team this year, they won a Think Award at a competition, and it's because they were recognized for having, they had, I believe it was 15 autonomous codes written, so they could decide in the moment which would be the best to use in conjunction with their alliance partner. So let's say, for example, if the goal was to pick up that plate or that plate on the end of the table, there's no point in our team picking up both plates if that team is able to pick up that plate and the one across the way. Let them do that. So, but you would have to change your autonomous code in the moment in order to accomplish that. So I don't know if I answered your question fully, but there it is.
I was going to have another question completely off.
Yeah, go ahead.
Security, code security. You know, hacking and stuff by the other guy.
Yeah, so first off, that would be a violation of the spirit of the competition and would disqualify a team if they did that. And there's really no, it's all closed circuit, so you're dealing with a processor. The controls that we're using are closed Wi-Fi network, so in other words, it's paired from the processor to the controller. It's not open source, so not everybody can access what's on your robot. They would have to maliciously do it. And so, just in the spirit of the competition, that would be grounds for complete disqualification if that was discovered. Yeah. So,
Kids are kids.
Yeah, kids are kids, it's true. But, that's one of the things. I realize the world can be a tarnished place, but we try to instill in them a level of integrity so when they go out, they don't take the low road, they seek to pursue the high road. So some of the things that are common in this competition is helping out teams that are at disadvantage. So for example, if I had one of my teams who was very capable, identified an alliance partner who was lacking in skills, they would send over some of their better people, whether it's coders or mechanics, to help them through what they need to do to be successful. Rather than just say, it's really all about us and let them just, fend for themselves. So kind of would defeat the spirit of the competition in that regard. But anyway, so at the second level robotics and in the honors robotics, this competition plays a large part in driving the technology that we develop. It's really the whole motivation behind it, right? It's not just like in a little capsule or nutshell or a single standalone project. It's for a grander purpose, and that's the competition outside of school. Just a few closing ideas here. So that VEX Robotics, it's the largest competition in the world. There are over 22,000 teams worldwide, both middle school and high school. So even though there was a bit of a typo, and I apologize for it if that came as a misunderstanding from me, in your newsletter it said that we won the World Championships 4 times. The truth of the matter is we made it to the World Championships 4 times. So out of 22,000 teams, I had one team from Sparta make it all the way to the World Championships. And then in competition at Worlds, actually do quite well but not win it. And so by making it that far out of that number of teams, they put themselves in the top 1% of teams literally in the world by that accomplishment. So a couple last things. In the last 6 years, we produced teams that have ranked in the top 1 or 2% globally. Graduates of the program have gone on, as I mentioned earlier, to all of the major engineering schools in the country, including 2 military academies. I have a young man going off to West Point this year and another in his junior year at West Point. A young lady from last year at the Naval Academy. 2 years ago, we also had the opportunity to, so around the corner from my classroom, there's a room called the Life Skills Room, and it's where children with special needs literally learn how to live life. And oftentimes they come by my room and they look in and they're all a marvel at what's going on in there, but it's nowhere in their schedule to be able to do these kinds of things or experience these kinds of things. So I created a program, it's called Intro to Robotics for Life Skills, and I give these kids an opportunity to come in and do all of the things at their level of ability that we actually do during our regular Intro to Engineering or Robotics 1 classes. And that's been fairly successful. So I also run a club, after school robotics club, go figure, and it is sort of a culmination of all of those kids who've now gone through the program and still want to do more. And so it gives them an opportunity to go further and further with it. And then I also do Science Olympiad. Science Olympiad's a different sort of, it's again a competition-based after-school program where we do both science and technology events, and very much student-driven for the purposes of promoting STEM as well. Does anybody have any other questions? And that's it. That's everything.
Fantastic. I don't know about everyone else, but I am really impressed by, and nothing personal here, Frank. These two are very impressive with what they're doing for our youth.
Absolutely.
Fantastic.
We're gonna have the national, people figure it work.
Take pictures of that.
Let me, Howard, you want to grab these photos?
Yes.
I gave you the, here's your pen.
What do we do with you?
And I, by the way, I think I gave your check to the other Mark. I think they're all in the one envelope together, so don't try getting out of here. I'm still pretty fast. So,
Can you move the mic, please?
yes.
He's the biggest one.
Thank you.
And we'll get your wife up here.
Yeah, sure. Okay, man, take a few of these. Good, all right.
And I have to make one quick comment. He talked about this group playing with Legos. I think it was Lincoln Logs.
Yeah, I was gonna say.
Legos.
Or Rector set.
Erector set.
Erector set. Come on. Join us.
Rector set, not Legos.
There you go.
Thank you. Great. All right, thank you very much.
Thank you. All right, fantastic presentations by both of you.
Yes.
I sincerely appreciate it. I think that about wraps it up, the official part of the meeting.